So here in our first lecture on thermodynamics, we have our discussion on what energy is. Now, there are a couple examples of energy, and if I was there and if we were in class, we would do this nice little activity. But ultimately, energy is the ability to do work or produce heat. And this is something you talk about in physics, but energy is what allows things to get done. It is what causes things to be done. Now, work and heat are the two primary forms of energy that we're going to talk about in this class, especially in terms of chemical bonds and chemical reactions and things of that nature. Um, Energy does come in two basic forms. The first one being potential energy, which is, of course, technically defined as the energy of composition or position. Now, some of you may have heard of this in physics as the ball sitting on top of the hill, and then, it rolls down. Sorry, I'm trying to get myself in the little camera box. The ball sitting on top of the hill, and then it rolls down. It has a lot of potential energy up here at the top because it just happens to be at the top of the hill. One way we can think of potential energy is how much energy could the object potentially use. In terms of chemistry, potential energy is how much energy is stored up in the object based on the way it's put together. Like solids have more potential energy than liquids, and liquids have more potential energy than gases because of the way they're put together. Now, water behind the dam has a lot of potential energy. Bonds have more potential energy than atoms. Pardon me. Now, the other type of energy is kinetic energy, and kinetic energy is the energy of motion, energy of things moving around. Gases, particles zip around and move around a lot. So, kinetic energy. Gases have way more kinetic energy than things like liquids, and liquids have more kinetic energy than things like gases. I like to think of kinetic energy as your more random movement energy. Now, they are related. They are two halves of the same thing. For example, as we raise something up, it does have a lot of potential energy. So you may notice that we've got this little we've raised this little block up. So it's got lots of potential energy because we've raised it up. And then when we drop it, it changes into kinetic energy. All that potential energy changes into kinetic energy. Now, there are 6 forms of energy that we are going to talk about. One of them is chemical energy, and this is potential energy that has been stored in bonds in some type of way. For instance, in photosynthesis, solar or radiant energy is stored in glucose, in that form of chemical bond. This is definitely a type of potential energy. Then, of course, there's work or mechanical energy. This is a style of kinetic energy in the fact that it is energy of motion, but it's all directed in the same direction. Wind, cars, all of those are kinetic energy because they're moving, but it's all in the same direction. And then, of course, there's what we call thermal energy. We will think of it as heat, even though heat's a verb, not a noun. Thermal energy is another type of kinetic energy, but it's more random kinetic energy of particles just randomly moving around all over the place, and the resultant friction from those particles running into each other and their surfaces interacting. Then, of course, there's radiation, light energy, and this comes from energy moving along the electromagnetic spectrum or through those photon particles, things we've discussed before. X-rays, visible light, sunshine, etc. All those are types of solar energy, things like that. Electrical energy is another type. Batteries, electrochemical cells, I'm trying to think of something that's electrical energy off the top of my head that it's really just the movement of electrons and any way that you can get electrons to move, and other than batteries, I can't really think of it, or electrochemical reactions, I can't really think of any. Now, of course, there's nuclear energy, which is energy stored inside the nucleus. These are examples like fusion in the sun and fission in nuclear power plants. Now, the difference between nuclear energy and chemical energy, is that nuclear energy solely has to do with the nucleus, whereas a chemical energy has to do with the bond itself. So you break a bond, pshaw, energy is released. I'm sorry, you break a bond, you have to put energy in, but there is energy inside a bond. But you break a nucleus, you're talking about breaking one solid single thing, and so much more energy is released. So nuclear energy, more energy is released than in a chemical bond or chemical energy. Okay, and here's just a nice little graphic to help you keep them straight. Okay, and that should be in your notes too. Now, there is a law of conservation of energy. Energy cannot be created or destroyed, and energy can only be converted. This is because the energy in the universe is constant. We had a discussion the other day that the universe is infinite, and the universe is indeed not infinite. Space is infinite, but the universe is composed of a finite amount of stuff and energy. So energy cannot be created or destroyed. You may put energy in, for instance, we put electricity into a light bulb, but not all of it comes out as light. Some of it comes out as heat too, which is why I burned myself when I tried to change the light bulbs in my kitchen the other day. It was very unpleasant. Okay, so this style of converting energy from one form to another, this is something we use constantly, consistently. In fact, it's kind of the basis for, life. We do want to convert one form of energy to another form of energy. The root of all energy on Earth is, the sun. Okay. Here's an example of how energy is transferred. You may put in 100 units of energy from gasoline. You'll lose about 3 units to friction from the pistons, about 6 units to just pumping combustion air, 25 units is usable as horsepower, about 29 units is lost through cooling, another 4 units to the engine, 33 is lost to exhaust, blah, 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 blah. So you never have complete 100% useful energy. Okay, so energy is always converted, but it's always conserved. We could always account for it. If we had the best instruments in the universe, we could always figure out where it's going. But we generally operate under the assumption that the energy is indeed going somewhere. Okay, now what I'd like you to do is I'd like you to work on the 2 computer activities that are at the end of your notes. Okay, now I want you to keep these as they are part of your notes. You may have some trouble with the PhET activity. When it comes to the PhET activity, these links are both on Google Classroom, but if you have trouble with the PhET activity, download it, put it on your desktop, right-click, select Open, and then you may have to put in admin certification, which means you'll have to ask me or the substitute to put in username and password to get it to open. Okay? So, as always, if you have any questions, please write them down and we'll talk about them in class.